Hello and welcome to our lesson on generalizing integration rules. Specifically, we're going to look at generalizing our power rule, the rule for integrating e to the x power, and then the rule for integrating 1 over x. Those are x to the n, e to the x, 1 over x. How do we generalize those rules so that if x becomes something else, we can still integrate? Okay, so we're going to start by considering the integral of x to the fourth. So remember, when we're integrating, we're looking for the original function. What we're given here is the derivative. So the derivative of some function gave us x to the fourth. So we're looking at x to the fourth power, the power rule here, undoing our differentiation power rule, which says to multiply and subtract 1 from the exponent. We're going in reverse. So we know that this would be x to the, if we add 1 to the exponent, x to the fifth, and then we divide by that new exponent of 5, and then we add on our constant of integration, and we're done. That would be the antiderivative of x to the fourth. That's the original function or family of functions that produces x to the fourth as the derivative. Now I prefer to write the coefficient as 1/5 x to the fifth instead of that fraction, but either way would be fine. Now remember, if you wanted to double check your work, we take the derivative of this antiderivative and it should take us back to the integrand. So let's do it. Let's just double check. If I took the derivative with respect to x of 1/5 x to the fifth plus c, then I should get back to x to the fourth, and in fact I do. So if I was to multiply here, 1/5 times 5 is going to be 1, so 1x to the 5 minus 1 would be 4, and then the derivative of the constant just becomes a 0. So again, we're in good shape. If I took the derivative of my antiderivative, I get the integrand, so we're good. Okay? Now what we're going to be looking at is not like x to the fourth power, but maybe something else like 3x squared plus 1 to the fourth power. How do we differentiate this composition of functions? Can we just use the same power rule? Well, instead of x to the fourth, if we have 3x squared plus 1 to the fourth, let's go ahead and try to just integrate this. Did I say differentiate? I don't know. Let's go ahead and try to integrate this the same way we integrated x to the fourth. But instead of writing an x here, let's replace that with 3x squared plus 1. Okay, since that's what's happened in our integral. If we do this exactly the same way, again, instead of x to the fifth, we're looking at 3x squared plus 1 to the, again, add 1 to the exponent to make 5 and divide by the new exponent of 5, and then add on the constant of integration. Or again, I could make this 1/5 times 3x squared plus 1 to the fifth power plus c. Is that going to be the correct antiderivative? That means if we take the derivative of that antiderivative, do we get back to this 3x squared plus 1 to the fourth power? Well, let's check. Let's differentiate with respect to x 1/5 to the 3x squared, or times 3x squared plus 1 to the fifth power plus c. If I take this derivative, using my power rule here, 5 times a fifth again makes 1, and then I would have 3x squared plus 1 to the 5 minus 1 is the fourth power. And then because, again, this is a composition of functions, I have to multiply by the derivative of my inner function. So I have to multiply by the derivative of that 3x squared plus 1, which would be a 6x. And then the derivative of the constant is 0, so we're good. That's going to be our derivative. Now if I go back and compare, we're close, but we're not quite correct here. The 3x squared plus 1 to the fourth power, that is in our integrand, but this piece is missing. This factor of 6x is missing. The derivative of that inner function isn't there, which means this isn't correct. If I take the derivative of my antiderivative and I don't get back exactly what I started with in that integrand, then I did not do this correctly. I did not integrate correctly. So since this does not match this, this is not correct. So what do we do to make this correct? Well, if we're dealing with a composition composition of functions like we have here, remember our chain rule we used to generalize our differentiation rules here? It's the same sort of concept. We're trying to undo the chain rule, right? We're trying to integrate something where the chain rule was applied. Well, if it's a composition of functions, if the chain rule is in there, then we should see the derivative of our inner function in that integrand. So if I want to, let me get a different color here. If I wanted to integrate something other than just an x to the fourth, something like, let's say, u to the fourth power, anything other than x, the only way for me to do this is if the derivative of that something, du, is a factor of that integrand. Now when I go to integrate, I'm still using my power rule. So I would still have u to the fifth power divided by 5 plus my constant of differentiation, or of integration. Sorry, I keep mixing those words up. Right, so this piece here did get us this correct part of the answer, but in order for us to do it, we have to have this as a factor of the integrand. So the derivative of the inner function, in this case I'm calling it u, has to be there. So if I wanted to apply this to this problem, to be able to integrate this problem, what I need is the integral of 3x squared plus 1 to the fourth power multiplied by the derivative of the inner function, which is 6x. Remember, this whole thing, that's what has to be there, dx. If I found that integral, then I use my power rule. I apply my power rule here, just like we did a few seconds ago, and we get that 1/5 times 3x squared plus 1 to the fifth power. That's going to be the correct, plus c, would be that family of antiderivatives, okay? So if we see a composition of functions, remember the chain rule says multiply by the derivative of the inner function. Well, if this is our derivative here, then that derivative of that inner function needs to be there in order for us to work in reverse and integrate. Okay, so when we are generalizing our integration rules, we can only apply these generalized integration rules to, let's just say, u. So not x, but or not x to the n, but u to the n. Not e to the x, but e to the u. Or not 1 over x, but 1 over u. We can only apply our rules if du, the derivative of that function, is a factor of the integrand. So u is going to be like the outer function, okay, the outer function being like x to the fourth in this one, and then du is the derivative of that inner function, so 6x on that example we looked at. Okay, so let me show you the generalized form of our rules. We said power rule for integration, if I have x to the nth power, that I would undo my power rule for differentiation, add 1 to the exponent, and divide, add on the constant of integration, we're good. Well, if instead of x to the nth power I have u, something else, anything other than x, like x plus 1 or x squared or 5x minus 1 or whatever it is, I'm still going to use my same rule. I'm going to take the base of that power, add 1 to the exponent, divide by that new exponent, and that base doesn't change. Okay, same power rule, but in order for us to apply it, du, the derivative of that inner function, has to be a factor. Okay, and the same thing here. We know that the integral for e to the x is e to the x plus our constant of integration. If it becomes e to the u, so this is e to the x here, becomes e to the u, anything other than just an x squared, a 7x minus whatever it is, okay, we're still going to apply the same rule. The integral for e to the u is still going to be e to the u, but we can only apply that rule if the derivative of u is a factor of the integrand. Okay, so we need for that to be a factor, but it's not going to affect our rule. Notice the rule is the same, right? This rule here, that's the same rule that we see here. It's just a u instead of an x, but we can only apply it if that derivative of that inner function is there. Okay, same thing here. We have e to the x, e to the u, right? So one more. If we're taking the integral, finding the integral of 1 over x, 1 over x becomes the natural log of x. So if it's 1 over u, it becomes the natural log of u. Okay? Again, same exact rule. If 1 over x is natural log of x, 1 over u is natural log of u. But we can only apply that rule if the derivative of u is a factor of that integrand. Okay? So 3 rules we've talked about before, just replacing x with a u, and applying the rule as long as, if and only if, the derivative of u is a factor of the integrand, if it's multiplied by the function. Okay? So let's try it, for example, here. We're going to do a few where we integrate u to the nth power. So this is a generalized power rule for integration. So if I want to integrate not x to the third power, but 7x minus 1 to the third power, then the derivative of that inner function, 7x minus 1, has to be a factor of this integrand. So the derivative of 7x minus 1 is just 7, and I see that here. We are multiplying here by 7, so we're good, which means I can apply my power rule to this portion. Apply the power rule. Okay, so this becomes 7x minus 1, add 1 to the exponent to make a 4, and divide by the new exponent, add our constant of integration. Done. That's it. Okay, now I prefer again to write this as 1/4 times 7x minus 1 to the 4th power plus c, but either one of those would be a perfectly acceptable form of the answer. Now, if that feels weird to you, remember, you can always check your work by differentiating. If you take the derivative of your antiderivative, you should get back to your integrand. So let's just pretend, right, I was unconfident here. I wanted to check my work. Let's take the derivative with respect to x of 1/4 times 7x minus 1 to the 4th power plus c. If I do this, I'm going to multiply 1/4 times 4. That's going to give me a coefficient of 1. And then it's 7x minus 1 to the 4 minus 1 would be the third power, multiplied by the derivative of the inside, which would be 7, and the derivative of the constant 0. So it's perfect. What I have here matches what I have here. So we're good. We integrated correctly. Okay, so if you want to check your work, you can always differentiate your antiderivative and make sure you get back to your integrand. Okay, let's try it again. Now this one doesn't look like a power rule, but it is. I'm going to start this one by rewriting my integral. I don't like those radicals. I'm going to make it a power instead. So this is the same as the integral of 2x times x squared minus 1 to the 1/2 power. And again, my power rule. So this is my inner function here, so let's just call that u. The derivative of the inner function has to be here in order for me to use this general power rule. So the derivative of x squared minus 1 is 2x, and that is here. There's my du, so I'm in good shape, which means now all I have to do is apply the power rule right here. So apply the power rule right there. So this becomes x squared minus 1 to the, add 1 to the exponent, so 1/2 plus 1, 1/2 plus 2 over 2 becomes 3 over 2. And then divide by that new exponent, 3 over 2, and then add on the constant of integration, and then we're good. Now it's not really proper to leave a fraction in a fraction, but dividing by 3/2 is the same as multiplying by 2/3. So I'm going to rewrite this as 2/3 times x squared minus 1 to the 3/2 power plus c, and we're done. That is the antiderivative of the function we started with. Let me just box this one in now since I didn't do that before. Okay, and then again, if you weren't sure, and you don't need to do this every time, but just so you can see how easy it is to check your work, take the derivative with respect to x of this antiderivative and make sure it takes you back to your integrand. So here, if we multiply 3/2 and 2/3, we're going to get to 1x squared minus 1 to the 3/2 minus 2 over 2 would be 1/2. And then multiply by the derivative of the inside, which would be 2x, and the derivative of the constant is 0, and again, what we have here matches what we have here, and so we're good. Okay, so we've verified our work. I guess I should just leave my verification here. I was going to erase it, but it looks so nice. Okay, so there it is. Now I'm not going to do that every single time, but again, if you're unsure about what you're doing, take the derivative of your antiderivative and make sure your work is correct. All right, let's try a couple more. So here, again, we have this composition of functions, our outer function being something raised to the negative fourth power, our inner function, let's call it u, 3x to the fifth plus 5. The derivative of that inner function needs to be a factor here, and it is, because the derivative of 3x to the fifth plus 5 is going to be 15x to the fourth, and that's what we see here. There's the derivative of u. So what I need to do is just apply my power rule right here. So apply my power rule. And I'm looking at 3x to the fifth plus 5 to the power of negative 4 plus 1 is going to make a negative 3. Divide by that new exponent, negative 3, and add on our constant of integration, and we're done. Now I would prefer, again, not to leave the negative exponent here, so I'm going to actually move this negative, although the negative could stay, I'm going to move it out in front. We're going to leave off with 1 in the numerator, and 3 is going to stay in the bottom there. We're going to move the 3x to the fifth plus 5 to the bottom to make that a positive exponent, and then a plus c. So now we're good here. Okay, and if you wanted to leave the negative, you could, but I don't know, it just looks a little weird sitting there on the bottom of the fraction, but it's fine. Okay, so there's multiple forms of that correct answer, but there you have it. And one more. Now this one is kind of like, I think, example 2. I would rewrite this. I don't want this quotient in here if I don't have to deal with it. So I'm going to make this the integral of 3x squared multiplied by x cubed minus 5 to the negative third power. So this would be like my inner function here is going to be x cubed minus 5, that's u. The derivative of x cubed minus 5 would be 3x squared, and I see that here as a factor, so I'm in good shape. I just need to apply my power rule right here. So this becomes x cubed minus 5 to the negative 3 plus 1 is going to be negative 2. Divide by that exponent of negative 2, add on our constant of integration, and we're good. So again, that would be an acceptable form of the answer. I'm going to rearrange this. Negative is going to come up here, leave the 2, move the x cubed minus 5 to the bottom of the fraction to make that exponent positive. To me, this just looks a little better, but technically both of those are acceptable. Okay, so I'm going to not forget to box in my answer. And now, I want to draw your attention to this one. See if you notice anything that's different about this one. Looks like a power rule problem, composition of functions like we've been doing, but there's an issue here. So if I'm looking at this inner function, 3 minus 4x squared, the derivative of that inner function should be a negative 8x, and that does not occur here. So this is not, well, I can't write. This is not du. It should be, du is supposed to be, it should be, excuse me, a negative 8x. So if du is not a factor of the integrand, you saw what happened in that very first example. Let me go back here. If that's not a factor of the integrand, like in this example right here, then when we go to integrate, we don't get the correct answer, right? This antiderivative here, or when we took the derivative of the antiderivative, we did not get back to the integrand. This was not correct work. So if that factor of du is not there, we cannot apply our generalized rule. So I can't apply my generalized power rule in this problem. Does that mean I can't integrate this problem? No, it just means I have to do something else. Luckily, I know how to manipulate this so that I can try something else. So what I'm going to do is I'm going to expand this product. So I have negative 8, and then I have 3 minus 4x squared being squared, which means it's going to be multiplied by itself. And I know how to multiply, so if I find this product, I'm looking at 9, and then a negative 12x squared and a negative 12x squared, so a negative 24x squared, and that's going to give me a positive 16x to the fourth. Now I just need to distribute the 8. So I have negative 72 plus 2 carry the rest, 192x to the second power, minus 8 times 16 is going to be 128 x to the fourth. And now I better verify my work because I don't want to mess up on something silly. And then 8 times 16. Okay, good. I can multiply. Yay. All right. So if I expand this out, this is really what I'm trying to integrate here. That doesn't require any fancy generalized rules. So let me rewrite this integral. This is the same as trying to integrate negative 72 plus 192x squared minus 128x to the, not the fifth, but the fourth power. And now I can just use my sum and difference rule. I can just integrate each of these three pieces separately. So this is the same as the integral of negative 72 plus the integral of 192x squared and minus the integral of 128x to the fourth. Oops. Don't mind me while I fix my work here. I forgot my dx. There we go. Okay, so if I integrate, and you don't have to write this out every time, I just don't want to lose anybody, but I have my sum and difference rules. If I have the integral of a sum or difference, it is equivalent to the sum or difference of those individual integrals. So here, the integral for our constant becomes linear, so this would be a negative 72x. And then here, using our just regular power rule, we have 192 times x to the third power, because we're going to add 1, then we're going to divide by that new exponent, minus, over here, this is going to be 128 times x to the fifth power, divided by that new exponent of 5, and then we add on our constant. Now, I don't remember in the previous lesson if I left the 192 there. Let me just back up right here. I could have made this 192 times the integral of x to the second power, but when I go to take the integral, I end up with 192 being multiplied by that integral. So if you don't want to factor that piece out, then that's totally fine. I generally don't. I just leave it in there. But when you're first learning, sometimes you're like, wait, what? If it's too many steps in one, then don't mind me. All right, now I'm going to go one more because this actually simplifies. So we're looking at negative 72x plus, pretty sure, 192 divided by 3 is 64. So 64x cubed, and then this one obviously doesn't. So negative 128 fifths x to the fifth, and then plus c. And so this is the antiderivative of the function that we started with. Okay? So again, I just wanted to reinforce that you cannot use your generalized power rule if differentiate your composition if the derivative of that inner function is not a factor of the integrand. So if du is not a factor of the integrand, you cannot apply a generalized integration rule. Alright, so we did a whole bunch with the power rule. Let's just try a few with the other rule. Integrate using the general rule for integrating e to the u. So the integral for e to the u is just e to the u. But we can only apply that general rule if du is a factor of the integrand. So here's our u, right? Here's u as 5x. The derivative of 5x would just be 5, so we have it. Du is here. So then this is just going to be equal to e to the 5x, right? The integral of e to the u is e to the u. So the integral of e to the 5x is e to the 5x. And remember, if you're not sure, because some of you might be thinking, I know this is a reasonable thought, that 5 should be here as well, but it shouldn't, because that's the derivative of our inner function. But if you're not sure, remember, just take the derivative with respect to x of e to the 5x plus c. Does it get you back to what you started with? So the derivative for e to the 5x is e to the 5x multiplied by the derivative of that inner function, which would be 5, and then derivative of the constant 0, so that's 5e to the 5x, which is exactly what we have here. And if you had brought that 5 over, which is a common mistake to put that 5 in there, then you would have ended up with 25 as your derivative here, so it would not have worked. So just double check your work by taking, why did I erase that? This is my check of my work. And this is this, so we're good. Alright, let's try one more. So here, instead of E to the x power, we have e to the x squared power, so this would be u in this one. There's our inner function. The derivative of u that is going to be a 2x, and we see that multiplied here, so we're good. So the derivative for e to the excuse me, e to the u is just e to the u. So this is just going to be e to the x squared, and then we're going to add on that constant. And again, just double check your work, because it's so easy to do, especially with e to the x. Take the derivative with respect to x of e to the x squared plus c. Derivative for e to the x squared is e to the x squared multiplied by the derivative of that inner function, 2x, and then the derivative of the constant is 0. And this, again, exactly what we see here. So it's all verified. All right, two more. Integrating 1 over x. So when we're integrating 1 over x, remember the derivative of the natural log of x is 1 over x, so the integral of 1 over x is the natural log of x. Now if it becomes 1 over... Oh, why did I put x there? I meant to put a u there. My bad. I could fix that now. Typos, I tell you. 1 over u. Okay, if that's a u there, it's still just going to be the natural log of u. If it's 1 over x, it's natural log of x. 1 over u, it's natural log of u. But we can only apply that rule if du is a factor. So here, it might be easier if you recognize this is the same thing as 3 times 1 over 3x plus 1. Not necessary to rewrite this integral, but just so you can visually see that 3 that's in the numerator of the fraction is like multiplying the fraction by 3 over 1. Okay, so instead of 1 over x, we have 1 over 3x plus 1. So we're going to call this the inner function u. And the derivative of u, the derivative of 3x plus 1 is 3, and I see that here being multiplied, so there's du. So just like 1 over x, the derivative for 1 over u is the natural log of u. So this becomes, oops, let me go back to blue. This becomes the natural log of, and there's absolute value, remember, because it doesn't matter if we get the positive or negative, same thing, of 3x plus 1, and then we add on our constant, and we're done. That is it. And again, if you weren't sure, check it. Take the derivative with respect to x of the natural log of 3x plus 1 plus c. Okay, the derivative for the natural log of x is 1 over x. This would be 1 over 3x plus 1. Then we would multiply by the derivative of the inner function, which would be 3, and the derivative of the constant is 0, and we get exactly what we started with. So this matches this. Again, we are good. Okay? And then one more, same exact thing here. If it's helpful for you to see that 2x is being multiplied by 1 over x squared plus 1. You don't have to rewrite it like this, but if it's helpful to see it, so then instead of 1 over x, we have 1 over x squared plus 1, so this new inner function. And the derivative for x squared plus 1 is 2x, and we see that right here as a factor, so we're in good shape. And so this becomes... derivative for 1 over u is the natural log of u, so this would be the natural log of x squared plus 1 plus c. And that's it. Done. Again, take the derivative if you want to verify your work, but I promise it's going to be right. And now I got to box these in because somehow I started and then I stopped, and I got to be somewhat consistent. So there it is. Okay, only the 3 rules we have to worry about generalizing. There are other generalized rules, but again, not rules that we're going to have to worry about. So as long as you can apply these, and you should be in good shape. So you got enough, I think, to get going on your homework. But as always, if you have questions, you need extra help, then reach out. Until next time, take care.